Okay, let's dive right into this. Have you ever actually stopped to think about how your computer does math? I mean, all the way down at the microscopic, bare metal level of the silicon? Well, today, in this explainer, we are going to explore a hidden conflict raging inside almost every single microchip on Earth. It's a literal microscopic battle between two radically different ways of calculating reality: the FPU gambler and the ALU surveyor. See, we all kind of operate under this universally held assumption that computers are flawless, perfect calculators, right? You punch in an equation and the machine spits out the absolute, undeniable truth. But what if I told you that for the most advanced, high-stakes tasks we ask computers to do today, that perfect math is entirely an illusion? What if, at its very core, the physical engine driving your incredible technology is fundamentally just guessing? To break this all down, here is our roadmap for the explainer. First, we'll look at the myth of perfect math. Then we'll meet the gambler versus the surveyor. After that, we'll cover the wood chipper effect, breaking blockchain consensus, and finally, wrap up with the deterministic solution. Let's get right to it. All right, section 1, the myth of perfect math. We really need to shatter this hardware illusion. To truly grasp the stakes here, we have to look past the software and peer directly into the physical hardware making these calculations. And brace yourselves for this staggering statistic. Between 80 and 90% of modern AI compute cycles are actually just hardware-level approximations. They're not exact mathematical truths. When massive language models or super complex financial algorithms do their heavy lifting, they aren't handing you a concrete answer. They are fundamentally estimating the nearest possible truth just to keep up with the overwhelming volume of data. And this brilliantly illustrates our core point. Kyle McLean-Smith really hit the nail on the head here when he said, it's fundamentally an approximation system, not real arithmetic. Just let that sink in for a second. The absolute foundation of our most advanced computation isn't exact mathematics, it's an estimation system that is physically bound to make highly educated guesses. Moving along to section 2, gambler versus the surveyor. This is where the hardware clash happens. So you might be wondering, who exactly is doing all this guessing? Well, imagine two radically different, warring characters living inside almost every modern computer chip. On one side, we have the floating point unit, or what we'll call the FPU gambler. It is wildly fast, but it's lossy and probabilistic. When it hits complex continuous math, it essentially throws darts at a board using secret proprietary seed tables burned straight into the silicon by manufacturers like Intel or ARM. And because those tables are corporate secrets, different chips will actually guess completely different answers down in the decimals. Now, on the flip side, we have the arithmetic logic unit, the ALU surveyor. The surveyor is strict, it's exact, and it's completely deterministic. It performs verifiable arithmetic where 1 + 1 is exactly 2, every single time, on every single machine on Earth. Now, the gambler's guessing game relies on something called the IEEE 754 standard for floating point math. Because a computer obviously has limited memory, it can't store infinite decimals, so it constantly chops off tiny fractions, like just dropping the 23rd bit, to squeeze continuous numbers into fixed memory slots. In total isolation, dropping a microscopic decimal seems completely harmless, but in modern computing, billions of these microscopic rounding operations violently compound over time. It creates this leaning tower of cards known as non-associative drift. The associative property of math you learned in grade school, yeah, that literally breaks down in the hardware, meaning the exact math you rely on daily for your finances and data is secretly decaying. Which brings us to section 3, the wood chipper effect, where provenance gets absolutely shredded. Let's explore the devastating consequence of relying on this guessing hardware for data provenance, which is the exact origin and chain of title of our digital info. Researchers call this the wood chipper effect, and let's walk chronologically through how it goes down. Step 1, a system, let's say an AI, ingests exact human source data, like a copyrighted book or a sensitive financial ledger. Step 2, the FPU gambler encounters the complex math required to process it, and it violently approximates the numbers using those secret silicon tables for maximum speed. Step 3, because that math was a guess and not a precise, trackable calculation, the original data provenance is permanently destroyed. To really drive this home, I want you to think of the FPU gambler as a giant digital blender. You know exactly what perfectly good fruits went into the blender, right? But you absolutely cannot perfectly reverse engineer that smoothie back into those exact original fruits. The lossy math permanently shreds the mathematical lineage of the data. Human authorship, exact identity, and chain of title are just ground up into unrecoverable dust. Let's move to Section 4 and see how this builds up. Breaking blockchain consensus, where microscopic bugs become massive global network failures. So zoom out from a single chip and look at the world of decentralized finance and Web3. A blockchain is fundamentally a replicated state machine. That means thousands of independent validator nodes running on all sorts of different hardware across the entire globe must evaluate a transaction and arrive at the exact same absolute zero-tolerance post-transaction state root. They require absolute universal agreement. And the FPQ gamblers' tiny little decimal approximations, they are fundamentally incompatible with this kind of digital trust. If even one single node guesses slightly differently, consensus fails. Now, what's really interesting here is how systematically the FPU triggers these state root mismatches. Looking at these variance factors, it's not just one thing. It is a perfect storm. Differing CPU architectures, like x86 versus ARM, they just have different rounding behaviors natively. Compiler optimizations will silently reorder math operations behind your back. Operating systems handle floating point exceptions completely differently. And that constant non-associative rounding to fit the mantissa, it basically guarantees that nodes will calculate divergent results. When this hardware non-determinism actually hits a live blockchain, cryptographic consensus shatters instantly. The network simply can't agree on the truth, and that leads to catastrophic ledger forks that split the network and freeze funds entirely. We see this immense danger in systems that try to use continuous curves like OrbSwap's polar coordinates off-chain. If you bring that FPU math on-chain, especially during a massive financial panic where market liquidity is violently shifting around, those tiny floating point rounding errors compound into severe, non-deterministic drift. It fundamentally breaks the smart contracts accounting. All right, finally, Section 5, the deterministic solution. Here is how we restore digital truth. So, how on earth do we fix this invisible hardware crisis? Well, the ultimate fix requires a complete paradigm shift towards what's called deterministic execution. This is the strict, totally unbreakable rule that the same computation, given canonical inputs, must produce one exact protocol-recognized result on every single node, everywhere, no exceptions. We have to completely bypass the sloppy approximations of the FPU gambler and rely entirely on the exact, reproducible mathematical states driven by the ALU surveyor. So, the crucial point is the incredibly strict toolkit developers are adopting right now to force this exactness. They are actively banning floating point operations from consensus-critical code entirely. They're enforcing rigid constraints within WebAssembly virtual machines. They're rebuilding complex math exclusively using fixed-point integers. They are even replacing those continuous geometric curves with discrete pixelated Pell-Smith coordinates and using highly efficient LIFO ledgers to instantly verify digital truth without any ambiguity. But wait, what about AI? AI absolutely needs that FPU speed, right? Well, engineers have actually developed an ingenious bridge called the DVR wash cycle, decode, verify, rollback. First, decode. The FPU is allowed to rapidly generate a fast guess. Second, verify. A completely separate deterministic process replays it using fixed, exact mathematical parameters. And third, rollback. If the fast guess doesn't perfectly match the exact verification due to drift, it forcefully rejects the bad data and recomputes. It's a brilliant way to actively cleanse out the microscopic gunk, safely bridging probabilistic speed with exact hardware accountability. Which brings us to the ultimate question for the future of our digital world. As we continue to offload our finances, our complex legal contracts, and our creative legacies onto these machines, what standard of accountability are you actually willing to accept? Will you just settle for the FPU gambler's lossy guess, passively letting your data be shredded? Or will you demand the ALU surveyor's exact blueprint, insisting on undeniable forensic trust and strict accountability? The choice is entirely ours. Thanks so much for joining me on this explainer, and always keep questioning the systems you rely on.